Okay, boys and girls. Okay, today we will continue lesson number 13. Okay, we'll learn about center of mass. Okay, actually last week we learned about moments turning effect. We're also talking about center of mass. Okay, some of the question they won't tell us that where is the weight. They just inform you in the through the sentence, and then they didn't show in the diagram, and then they say that the beam having the weight of how many Newton, then they're pointing the center of mass as G. Okay, so today we'll talk more about center of mass. Okay, center of mass actually is a point that all the mass they concentrated to that point. Okay, or we say the mass or the weight they concentrated to that point. Okay, so at here all the mass they were concentrated at one point. That point we call as center of mass. Okay, every object got their center of mass. So center of mass sometimes we call it as center of gravity. Okay, center of gravity. Okay, so at here, center of mass is the point that the weight or mass will be pointing downwards, okay, acting on this point. So if let's say your finger, you're able to find the center of mass, and then you put your finger at the point, exactly on the point, so your finger will be giving a support upward force, okay? So if you're able to balance the object, that means that actually now your finger is exactly at the center of mass. Okay, so if you're able to find the point, then you put your finger at here. Your finger provided an upward force. It can be balanced it and hold it. That means that you are exactly finding the correct center of mass. Okay, how we find the center of mass? If the object is symmetry, okay, so that is very easy. Okay, so we can find by finding the intercepting the line of symmetry. Okay, for the first one, only one line we cannot know where is the center of mass. We need at least two lines. For example, you look at this, okay, the symmetry line, one line, two line. So with at least two line, we can able to find the point that intersect. This is center of mass G. So for the first diagram, actually from here, we still cannot know by using one line to find the center of mass, cannot. Okay, so what should we do? If let's say this one is like 2 meter, let's say, okay, 2 meter. So in the half of it, 1 meter, okay, we draw a line. So these two lines that intersect this point, the dot at here actually is center of mass G. All these points, when they intersect, this is center of mass G. Okay, for uniform and symmetric object easy. We just find the line that intersect, okay? The line of symmetry that intersect, then we can know. We don't need to do very complicated. So this is regular object or uniform and symmetrical object. Okay, until here, okay? Then we go to page number 2. Okay, teacher, if let's say irregular shape object, how should we do? Okay, how can we find the center of mass? Okay, now I'm going to show you this video. Okay, here.
Let us now see how we can find the center of gravity of an irregular object. Let us take an irregular cardboard and make 4 holes on all 4 sides of it. For this experiment, let us keep a plumb line ready for a rubber cork with a stand pin. Let us mark the plumb line by placing the pin in the first hole of the cardboard. In this way, let us hang the remaining 3 holes of the cardboard on the pin and mark the plumb lines with the help of a marker. Now, with the help of a scale, let us draw 4 plumb lines using a marker. The 4 plumb lines meet at a point. This is what we call the center of gravity. Through this activity, we can find out that the entire mass of this cardboard is concentrated near this center of gravity.
Okay.
Students, let us now see how.
Okay, so this is the method how we find the center of mass for the irregular shape object. Okay, we cannot using just now the method to find the line of symmetry because they are not a uniform and symmetric object. Okay, so for here, how we do this finding this center of mass? First, you have to suspend the card and make sure the card can be moved freely, does not stuck. It can be moved freely, and then we will make one hole at one corner lah. Okay, any point you can choose, any point. Okay, then what we need to suspend? We need to suspend a plumb line. Just now got mentioned plumb line. Okay, so this line is called plumb line. Okay, this one is called plumb line. It will always acting downwards because it's weight. Okay, the weight is pointing downward. And then we use a pencil to draw a straight line. So we use a pencil and draw the straight line. Okay, follow the plumb line and then we draw the straight line. Center of mass, we confirm it will be along this one. But any point, which point, at what point, we still don't know yet. By using one line only, we cannot know where is the center of mass. Okay, so like what I mentioned, we need at least two lines. So what should we do? We repeat the process, okay, repeat the step just now by using another hole. So maybe we can using this hole, okay, then we change our position and use the second hole. Okay, at here is labeled as Q. Okay, then do the same thing. Hang your plumb line. Draw the straight line using pencil. Then the point that intersect by these two lines, this is center of mass, or we say center of gravity. Okay, so we write down. This one is center of mass. Okay, is it okay? Okay, is it okay, dear? Okay, so at here, I think I got recording right now. I'm recording the video, right? I think so. Okay. Um, okay, here hole 1, then we change hole 2. If it goes to hole 3, hole 4, you'll find out that they will be passing through the center of mass. Okay, no matter how many hole or which point you use, at the end, they will pass through the center of mass G. Okay, we goes to the past year question right now. Goes to page number 3. Okay, here. So the diagram shows a flat metal plate that may be hung from the nail so that it can be rotated about any of the 4 holes. Okay, so here got 4 holes. What is the smallest number of holes from which the flat metal plate should be hung in order to find its center of gravity? In order to find the center of gravity, what is the minimum number of holes that we need? No answer? This should be easy. Any of you? How many we need in order to find the center of gravity? Do we need all the 4 points in order to find the center of gravity? Zihua correct. Emily correct. Thank you. 2 enough. At least 2, dear. So come back to here. At least 2. Actually, from here, we already know the center of mass or center of gravity. Then you're using the third point, 4 point. Doesn't matter. They were just passing through the same point. Okay. So at here. Okay, this is a uniform flat metal sheet that hanging freely from a nail at point A. A weight also hang freely, okay? Then one of the label point is the center of mass. Yes, when we hang like this from the one line only, we can know that center of mass actually is along this line. But at which point right now? What do you think? At which point actually is your center of mass? My dear, tell me your answer. Tell me, Angeline. Okay, correct. Okay, boys and girls, this question easy. Answer will be C. Why is C? You can trying to think from others' point at here when we hang it. Okay, I already draw it here. When let's say we change to another position, we make the hole, and then we hang the object here, the weight at here. Then we found out that it will passing through C. Okay, so this one need your imaginations. Need you to turn and then imagine. Okay, we goes to your next page. Here. Okay, try for this question. Where is your center of mass? Zihua, no. Like others, try. Xuan, try. Crystal, Emily, Megan. Zihua correct right now. How about others? Wrong also never mind, dear. Emily, no. Crystal, no. That's why I asked you guys to try. Okay, what I want to say? Okay, here the answer would be C actually. C is the center of mass. Okay, why? Teacher, why? Okay, if let's say you hang at here, it will be roughly like this. Okay, so this is your weight. So means that your center of mass must be A, B, or C. Must be. Okay. Then if we turn, okay, if we turn, so I'm trying to turn, then I hang from some point, certain point at here. Okay. So above the D point at here, I hang. Roughly, we will get a straight line like this. So that means that these two lines, we add it up together, they will intersect at point C. Okay, so that means that for this object, the center of mass actually is outside of the cup. So you cannot hang it using you cannot, what we say, balance it using your finger because it's out of the object already. Okay, so this is the center of mass. No matter how you're using the two methods that we mentioned just now, hang it and then draw the line, then we change to another position, then we change the line again. Okay, so we goes to the page 5. Okay, page 5. Stability. Okay. For this page, actually we can touch and go because there is none of the past year question is asking about equilibrium, neutral, equilibrium, stable, equilibrium, and unstable. But because we have to talk, is because later on we have to mentioning about stability. Okay. So for here, neutral equilibrium is the object, we push it, okay? It neither return to original position nor move further away. The center of mass does not rises or fall, okay? So you see, center of mass, no matter how we push it, okay, it moves. So center of mass still remain the same, okay, at the same height. So for stable equilibrium, okay, we push it a little bit, it will go back to original position. It will go back. Okay, so this one we say that is stable equilibrium. Okay, center of mass rise when it is displaced, but after that it will go back. Okay, it will go back. Unstable is when we push. Okay, it will move further away and will not return to original position. Center of mass will fall, okay, will be going down. So at here, this one is just touch and go to let you know that actually got these three type. Okay, for the first one, this one, you imagine, we push it like this, slightly push only. After I release my hand, okay, it will, what's going on? It will go back. It will go back to original position. So we say that this one is stable equilibrium. Okay. Then after that, second case, when we push it, it will fall. Okay, it will fall somewhere here. Okay, it will fall here. So this one, the center of mass will decrease. So just now it's at here, when it fall, is somewhere here. Okay, so this one is called unstable. The last one, we push in this way, push it. Okay, make it rotate left, right. So the center of mass height is still the same. So this one is neutral. Okay, so this one is just like knowledge. Okay,
So
so
if the height doesn't change, it's always neutral.
Pardon?
If the height doesn't change, it's always neutral.
Yeah, the center of mass height, yes, doesn't change. Then this is neutral equilibrium.
Okay.
Okay, so at here, the most important actually is on this patch. Okay, this is talking about how what is the factor affecting the stability. Okay, so when you're trying to fighting, of course, we don't encourage to fight. But if let's say somebody bully you, you want to defend, how to make sure your self stability is good, not easily to fall down. Okay, one of the technique is please make sure you open both of your leg. Okay, make sure your base area is bigger. Okay, so make you more stable. Okay, so which cone actually is more stable? My answer is B will be more stable. So open both of your leg. Okay, the base contact area should be larger. Okay, then how about the center of mass? Actually affecting by two. One is the base area, one is because of the center of mass. Okay, so for this one example, center of mass is here, B is somewhere here. You'll find out that A and B, their height of center of mass is different. So which one more stable? My answer is the B arrangement will be more stable. Okay, so at here the height of center of mass should be lower. Okay, make sure it lower so you will be more stable. Okay, this is the reason how they design. Okay, how they design the racing car. Okay, why the racing car they run so fast, the speed so fast, so high speed, but then they still stable is because they already know how to increase the stability. Okay, they make sure they're having the car having a lower center of mass. Okay, and then wider base. Okay, so we goes to your page number 7. Okay, a body will topple when the vertical line through the center of mass. Okay, from the center of mass, we draw a vertical line. If the line is outside the base, then object will topple. Okay, if inside the base, then it will be stable. Okay, so at here, we look at this. Where is the base? This is the base. Maybe I change another color. Where is the base? Here is the base. Here is the base, and here is the base. Okay, we look at the first case. Can you see that the vertical line that pass through the center of mass is inside the base? So in this case, the chair actually is stable. It will not topple. It's stable condition. Okay, second case. Okay, we slightly push a little bit. Okay, then center of mass, we draw a straight line, vertical line. We still find out that it will be inside the base. What does it mean? This case, actually, it will stable also. It will come back to original position. It will come back to here. After we release, it will come back to original position. It won't topple. Okay, but for the third case, can you see that here is the base, but the vertical line pass through the center of mass. This line is already out of the base. So for this case, the chair confirm will topple. So in this case, you write down unstable. Okay, then we look at the example of the bus. Bus at here. Okay, first case, this is the base. It will be stable because the vertical line is inside. Okay, second case, this is the base. Vertical line still inside, so this is stable. Third case, I increase the angle. Will the bus topple or not? You see, it's still inside the base. So this one at 30 degree is still stable. How about 45? This is the base. This is the base, but this is the vertical line through the center of mass. So in this case, 45 degree, the bus will be toppled. This will become unstable. Okay, bus will topple at 45 degree because the vertical line through the center of mass is already out of the base. Okay, is that clear? If clear, then we go to the past year question. Can you guys tell me which diagram shows the most stable arrangement? Correct. Correct. Easy. Okay, dear. Answer will be B. Because center of mass is lower. Center of mass is lower. But why not D? D, the problem is this is your base. It's already outside your base. So this one will topple. Okay, so this is not a good idea. We goes to question number 2. Okay, which object will fall over? Try. Which object will fall over? Crystal correct. Megan correct. Answer will be C. Okay, so if you draw it out, it is out of the base here. Okay, this one like this, we draw it out. The rest we found out that it's inside. This is the base. Here is the base. Here is the base, and here is the base. Okay, so this one is outside base. Okay, so answer will be C. Okay, number 3. A light aircraft stands at rest. At rest, that means that they are stable. At rest, that means that equilibrium balance. So it's stable condition. Okay, it stands on 3 wheels. Okay, which point could be its center of mass? What do you think? Which point actually is the center of mass? Correct, Emily. Angeline, correct. So dear, if stable, what does it mean? This is the base. Your center of mass must be inside, within the base. Okay, Megan, correct. So answer will be B. Okay, this one, answer is B. Stable, that means that the line should be inside the base. Okay, within the base. Okay, the center of mass. Okay, we goes to the question number 4. Point X is the center of mass of lamina in the shape of triangle. Initially, this triangle, here is the center of mass with with side of equal length. The top of triangle is cut. So right now, what I draw is actually the new shape. What happened to the center of mass? What do you think? Now our new shape is what I draw right now. What happened to the center of mass? Angeline, correct. How about others? Megan, correct. So correct. Okay, dear, answer will be A. So your center of mass, because you lose some mass at here. So that means that now your mass will be concentrated somewhere here, which is lower. Okay, which is lower than just now. Okay, so at here it will move downward towards to the bottom of the page. Okay, now it goes to the next page. Okay, a small pin is fixed to the edge of a bench. A triangular piece of cut with the small holes in each corner is hung on the pin from a corner A and allowed to settle as shown in figure. Plumb line is then hung from the pin and vertical line AP is marked on the cut. Procedure is repeated. Okay, so this one is first step. Procedure is repeated with the cut hanging from point C and vertical line CQ is marked. Okay, so this is the result. We get 2 lines. Okay, draw the vertical line that would be obtained if the cut were hung from point B. If I hung from point B, can you draw the vertical line? How I know where is the vertical line? Any of you know how to do? We don't have practical, but here theoretically, where the line should go to. Do you know about this? It should be easy one. Should be touch the intersection part. Yes. Okay, here it will be goes to this part. Okay. Why, dear? Because this point is actually center of gravity. Center of gravity. No matter how many points you draw, you use, at the end they will pass through the center of mass. So at here, your answer should be this. Okay, so this is answer 1. Clearly mark the center of mass by using the symbol of G. Yeah, I'm marking already. Using a dot, don't using cross. Okay, they ask you to dot, then you draw the dot. Okay, then we goes to B, related with the stability. Okay, we got figure 12.3 and 12.3A and B lah. Which one actually is more stable? What do you think? For my student, roughly like 50%, only 50% of them can answer this question. Zihua wrong. Angeline, no. Megan, no. Emily, no. Kristen, no. Okay, wait, I scroll up a page. Shuan, is it here? Okay, dear. Those who just now be, none of you answer correctly, leh. You know why? You know why your answer is wrong? I let you think. Let you think a bit. Until Shuan finish this one, then I go back to the page. You think why your answer is wrong. Then it answer to me. Explain to me why it's wrong. What is the reason? No, Zihua, no. Stability affected by what, dear? No, Angeline, no. Stability affected by what force? Not what force, what factor? Stability will be affected by what factor? Crystal, no. Hey, none of us answer correctly for that question. Xuan, is it okay for this page? Okay, Okay, dear, my answer is which one more stable? Actually, this one. Figure 12.3A is more stable. Why? Oh my God, teacher, why? Okay, stability affecting by one. What is that? Affecting by the base. Second, affecting by what? The height of center of mass. Dear, only these two. Okay, you look at this. This one, the first diagram, actually there is no mass at here. So actually the center of mass might be somewhere here. Might be somewhere here. Okay, I'm using highlighter somewhere here. Okay, it can be somewhere here. For the second case, we got a lot of load at here. So that means that it will make your center of mass higher position somewhere here. I'm using highlighter somewhere here. Center of mass will be somewhere here. Can you see that the second one actually is not that good in stability because it already getting higher center of mass. So the first one actually more stable is because lower center of mass. Get the idea there? It's because of the center of mass, the height of center of mass. If you got a lot of load at here, you are make your center of mass higher. Okay, it's okay? Yes or no? Yes, Crystal, okay already, So it goes to the C, Okay, another case here. Okay, tell me why. Correct, Zihua. Who else? Which one will be more stable? And which one will be 4 first? Megan, correct. Megan, do you know why? Emily, correct. Okay, here, which one will be 4 over first? Answer is block A. Reason is what? Reason is because of their base, okay? Smaller base. So, can you see that for B and C? Asking about stability. Okay, topper is also related with stability. So at here, one of the question is testing on you. Do you know about center of gravity or center of mass? The height actually is one of the factor. Another one is base area. Okay, so these two questions is related with the center of gravity stability. Okay, if no question, we go to the last page. Can we go to the last page? Okay, Megan, okay, Okay, dear. A student is sitting on a chair as shown in the figure 3.1. Can you estimate the mass of the students? Type your answer. Estimation. A student. Mass of a student. You are the student, so you write your mass. That is the answer. Zihua, you only got 35 kg. Seriously? 38? 38 also not enough, dear. 38? Are you 38 kg? You need to increase your mass. Megan, okay, Megan, 45 kg, acceptable. 50 kg, okay, makes sense. The, too less, 38. that is the primary mass. You need to eat more, balanced diet. You're only 12? You're only 12? 12 is year 6, Year 6 or year 7, You're already in year 10? Zihua, you're already in year 10, That means you jump a lot. Okay, dear, for this, we accept the answer 40 kg to 100 kg. Of course, there might be some special case like Zihua, okay? It's only 38 kg. And maybe your friends eat a lot of KFC, McDonald's, gain 100 kg. But this is not in the normal range, okay? Okay, dear. Here, which statement is correct for the mass of the chair on the moon and the mass of the chair on the earth? What do you think? 1, 2, 3, 4. Which one is correct? Angeline, correct. Okay, previously when we're talking about the mass, in physics, what is mass? Mass is amount of substance. Amount of substance. So it's not the mass that we know in our life 45 kg, then tomorrow become 48 kg because you eat a lot and so on. That is different thing. In physics, mass is amount of matter. It will always constant, always constant. So at here, it will be the same. Okay, answer is the third box. You take the third box. So the mass is always constant, no matter on the moon or on the earth. Amount of matter is something like, you got 2 hands. Then you go to the moon, you're also having 2 hands. That is mass. In physics, mass, amount of substance. Okay? So, B. The student tip his chair back. Okay, what do you think? Will the student topple or not? Oh, but here, the question is already tell you. Explain why the chair will topple over backwards. It will topple. Okay, you may draw on the figure 3.2 as part of your answer. This one easy lah. Okay, dear. Like just now what we say, this is the base. Okay, then you draw the vertical line through the center of mass. This is center of mass. You will find out that the center of mass actually is out of the base, outside the base. Okay? Okay, here, vertical line we draw already. Okay, center of mass outside. Base area of chair. Okay. Okay, is it okay for this question, for this worksheet? Lesson number 13. We complete the chapter 4. Now we are going to enter chapter 5. Lesson number 14. If okay, then we go to the next lesson, next worksheet. No response. Is it okay? Megan, okay. Emily, okay. Who else? Crystal, okay. Xuan, is it okay, Xuan? Lisha say? Xuan, okay. Okay. Megan, okay, Megan? Okay, dear, we go to the next chapter. Next chapter is actually chapter 5, force and metal. Okay, here, force acting on the solid, it can change the size, change the shape, okay? But you always remember, no matter how mass is always constant. So some of the MCQ question, they're trying to trick you. They're trying to say that mass is force can change what? To move, then change the mass. No. If they're talking about the mass, it's always constant. Even force we are acting on the object, we won't able to change the mass. Okay, this one. So here, we learn about the spring. Okay, when the spring doesn't take anything, there is no load on it. If there is no load on it, we measure the length. The length we call it as original length. Okay, maybe I can label the symbol like this, original length. If we start to hang some object on some load, okay, acting on the spring, of course the spring will extend. It become longer. So at here, we measure the length again until here. This is called new length. Okay, maybe we can label as n new. Okay, so the extra new length minus original length, the answer is actually called extension. Extension, we got the symbol as x. X is our symbol. Extension symbol is x. So how we find extension? Using your new length minus your original length. This is extension part. Okay, so if we do some experiment, 1 Newton, 2 Newton, 3 Newton, 4 Newton, we plot the graph 1, 2, 3, 4, then we plot the graph. We found out that at the first part at here, in the graph, in the experiment, we can get a straight line pass through origin. Straight line pass through origin here, straight line. Second, pass through origin. These two from the graph, we know that extension x actually is directly proportional to force. How I know it's directly proportional? Straight line, and then the line is passed through origin. So I understand this relationship is called directly proportional. Okay, so Hooke's law. Hooke's law said that extension of the spring is directly proportional to the force. X is directly proportional to the force. Provided, okay, this one, I don't want elastic limit. Elastic limit is actually used by SPM, Malaysia government syllabus. We call it as elastic limit, but in our IG, we call it as limit of proportionality. This one you cancel, change it to limit of proportionality is not acid. Okay, so there is one point. The point here, P point, we call as limit of proportionality. Hooke's law only apply until this point. That means that this one until here, this region we obey Hooke's law. This region we obey Hooke's law. But after this region, can you see that it's no longer a straight line? It starts to curve. So this point, after point P, after this point P, it doesn't follow Hooke's law. So you can imagine one spring, it got its limit. One is be permanently deformed. So the point that, or we say the force that maximum that we can apply for the on the spring, so that at the end it can go back, is until this point, limit of proportionality. But after this point, you will find out that the graph line is actually no longer a straight line, continuous straight. No, it will be curved. Okay, it will be curved. When it curve, it will curve towards to your x extension. Why? Small force meaning that you see just a small amount of force, but it extend a lot. Small force apply, but it extend a lot. Okay, it extend, go up a lot. So we goes to your page number 2. Until here, is it okay? Okay, we goes to page number 2. Okay, from the graph of extension x against f, the portion of the graph 0 to p, okay, so here 0 to p, that means this region. This region, what apply? Hooke's law apply. Okay, we apply Hooke's law. So we write down Hooke's law. Okay, we apply Hooke's law. Then after that, beyond the point P, Hooke's law does not apply anymore. Beyond the point P, what is point P? Point P called limit of proportionality. Any force beyond this point will cause the spring to be permanently deformed. Okay, after this point P, your spring is spoiled already. Okay, so what finality, the maximum force up to which extension is proportional to the load. That means that this one, extension proportional to the load. Load is force, load is the force. So the maximum force that we still obey Hooke's law. That is the limit of
When it is
proportionality. After
permanently deformed, no matter what we do, we also cannot get back to the original state.
yes, cannot. Yes, it's already spoiled. The spring is already spoiled. When it goes greater than the point P, your spring is spoiled already. It will be longer than original length. Okay, here I want to emphasize, when you do the partial question, you must be careful with the graph, because we got two type. They can exchange their exchange their axis. So for this one, extension, this one is force. Here is force, then this is x-axis is extension. They can exchange the axis. Okay, for the O to P part, actually it's the same. Looks like the same, nothing changed. But what is the difference after point P? That will be different. Okay, for the point after point P, I told you just now, small force, your spring can extend a lot. So you will be curve towards to your x. So for the first diagram, curve towards to your x. Curve towards to your x. It's already spoiled. Small force, it extend a lot. For the second diagram, extension is on your x-axis, so it curves like this. So this is the part that I want to emphasize. So when you do the question, so you need to look at it. Where is your extension? It will curve towards to your extension after what? After the point P, limit of proportionality. Okay, what is the formula for us to do calculation for Hooke's law? We understand that F directly proportional to X, or X is directly proportional to X. So in physics, this is called directly proportional. We want to make equations, we need to change it into equal. But when we want to make it into equal, we cannot just change f equals to x, cannot. We need to put a constant value. So we put a constant value k. So at here, Hooke's law formula is f equals to kx. F equals to kx. So this is an important formula for this topic. F equals to kx. F is what? It's the force that we're acting on the spring. So this is in Newton. Sometimes they don't tell you, they give you mass, but we can understand force is weight. We can using W equals to mg to do calculation. And the G at here is 9.8 Newton per kg. Okay. Sometimes they didn't give you the force directly, they give you the mass. So please, we have to calculate the weight. Okay, we talk about the x extension first. Extension is we measure, it can be measured in cm or m. M is SI unit lah. But if the question doesn't really specific one SI unit, doesn't matter. You can be measured in cm. Okay, what is the unit for spring constant? What is this unit? I rearrange for you. K equals to F over X. Do any of you know what is the unit for spring constant? In physics, we study smart, derive it. Don't everything memorizing, but we derive it from the formula we can know. Any of you can tell me? Zihua correct. Any others? Correct, Angeline, very good. Okay, Newton per cm or Newton per meter. Correct. So dear, can you see that this is in Newton, this is in cm or Newton per meter? Okay, we don't need to memorize, but we can derive it. Okay, so boys and girls, look at here, example past here. A spring have an unstretched length. Unstretched, that means the original length. So this is original length. When a force level 60 Newton, this is the force, the length increased to 5 cm. So this is your new length. The limit of proportionality is not exceed. That means that we apply Hooke's law. Hooke's law can be applied at here. Hooke's law. Okay. Hooke's law can be applied. That means that F equals to Kx. We can use this formula. What is the spring constant? Question wants you to count K. Can you guys try? Okay. Angeline, correct. Zihua, no. How about others? If you got no idea, I draw the diagram for you already. Original length is 3 cm without hanging any object. Then we hang the 60 Newton. Then it will increase to 5 cm. Okay, so we can apply Hooke's law because we still not exceed the limit of proportionality. Where's the others? Crystal, Emily, you all? F is 60. K, we don't know. Extension. Extend 2 cm because we're using 5 minus 3. Okay, so at here 5 minus 3. So your K should be 30 Newton per cm. Because this one we are using cm. Here is in Newton. So answer should be Newton per cm. Answer is donkey. Okay, so we go to your next page, page number 3. Okay, next question. Teacher, so what is spring constant? Why we need to calculate spring constant? Is the spring constant bring any meaning? Yes, let's go. Is it okay? Can we proceed to the next page? Crystal? Xuan? Okay, we go to the next page. Okay, what is spring constant? Spring constant actually measure the stiffness of the spring. Stiffness is something like hardness of the spring lah. Okay, so the K value can we can know from the K value, we can know that is it this spring easy to extend or actually harder to extend. Okay, so look at here, spring constant. To understand the meaning of spring constant, we look at this diagram. Okay, I want to calculate the gradient. Your mathematics, do you know how to calculate gradient? Gradient is y2 minus y1 divided by x2 minus x1. Okay, here because we know that this point 1 meter, so you're using this point as one of the point 12.5. Then another point at here, you're using 0, 0. Then this one is x1, y1. Here is x2, y2. Can you calculate the gradient for me? Using mathematic way, calculate gradient. After you calculate the gradient, can you tell me what is the unit for the gradient that you get? Yes, correct. Okay, for the spring A gradient, I get 12.5. What is the unit? Okay, because y-axis at here, this one is y-axis, unit for y-axis is in Newton. According to the graph, y-axis is in Newton. Then x-axis is actually in meter. So your answer, Zihua, your unit is wrong. Your answer at this question should be Newton per meter. Okay, can you calculate the gradient for spring B? Gradient for spring B. You guys able to get the same answer as me? 75 Newton per meter, correct. Okay, dear, what is this meaning? Okay, here, Newton per meter. What is this unit for? What physical quantity having the unit Newton per meter? Is what we are learning today, right? Spring constant. Spring constant unit is called Newton per m or Newton per cm. So for the graph, fx graph, when we calculate the gradient, we are calculating the spring constant. Okay, gradient of the fx graph. We will get the gradient, actually we're getting the spring constant. Okay, so what is this meaning? Okay, spring A, in order per meter, meaning that here per meter, in order to extend every 1 meter, we need how many Newton? We need 12.5 Newton. So at here, K equals to 12.5 Newton per meter. Per meter, this is the meaning per meter. That means every 1 meter, I need 12.5. So spring B, every 1 meter, I need 75 Newton. Spring constant value can tell us that actually spring B is stiffer spring. Stiffer means what? Harder to extend. You want to extend 1 meter, you need to apply 75 Newton, you're only able to extend it to 1 meter. So spring B is actually harder spring, stiffer spring. Okay? A larger value of K indicates that a stiffer spring. Harder to extend. Okay, until here, is there any question there? Any question? No question. We go to the page number 4. Okay, here again, I want to emphasize they can change their axis. They can exchange their axis. So just now what we study is called fx graph. This one is called fx graph. Okay, fx graph. So we found out that the gradient actually is the spring constant. Because our spring constant is actually force divided by x. How I know? F equals to kx. I rearrange the k, f over x. So when I find gradient from this graph, I'm getting f over x exactly the same. So for fx graph, I'm finding gradient. Actually, I'm finding the spring constant. Okay, dear, need to be careful. If the graph right now is called extension against force, can I still saying that the gradient actually is my spring constant? No, you cannot say so. Okay, gradient is actually, from this graph, is x over f. Why? Because gradient is y against x. In your graph at here, what is your y? Is your extension x. What is your x? Is your force. But x over f, x over f, this is not your spring constant. Your spring constant should be opposite way, upside down. Okay, it should be f over x. So if we want to find the spring constant for this question, you should 1 over the gradient. Okay, is that clear? I show you the two different type of case. Not all the graph you find gradient is spring constant. No, you have to be careful. What is the axis right now? Okay, any question? Before we go to the past year question? Any question, dear? If no question, give me response, then we can try with past year question. Crystal, okay, Megan, okay. Emily, Angeline? Okay. Okay, dear, come. Okay, here different load hung on the spring. The diagram shows the length of the spring with and without the load. What is the extension of the spring when the load is 400 Newton? Okay, easy. Tell me the answer. Correct, Angeline, correct. How about others? You need to really understand how to find extension. Most of the students, they will give me the wrong answer is because they're trying to using 65 minus 40. But no, dear, no. Extension is your new length minus your original length. The 20 is original length without any load. Emily correct. Zihua correct. So for this question, 65 minus 20, 45 cm. Answer donkey. You don't trying to using 65 minus the 40. The 40 at here is just one to confuse you. Okay, there we go to your next page. Okay, question number 2. Different weights are hung from the spring. The diagram shows the original length. Then different right now is they give you the length. Oh, okay, they didn't give you the W. They want you to calculate what is your W. Can you guys try and then tell me your answer? Angeline, correct? Good job. How about others? What is your W? How I know, teacher? If you're using F equals to Kx, I don't know the W. Teacher, I also don't know my K. Even though I know that my extension is 20 cm, but I don't know my K. How can I find my K, dear? Give you some hints. You don't know the K, then you find the K first. How can I find? Using this one, the non-case to find the K. So you can using like this, F equal to Kx. You're using the 20 Newton equals to the K times the extension, 25 minus 15. So it's actually 10. K is actually 2 Newton per cm. You can using this case to find your K first. Okay, because this is the same spring. Okay, we just exchange to a heavier load only. So the K won't be changed, okay? The K won't be changed. So we continue using the K. Megan correct, Emily correct. So at here, the K is 2 times 20. So at here, your answer should be 40 Newton. Answer is C. Okay, but this is physics way. Physics way. We find the spring constant, apply in the formula. But I can tell you another more easier method. Okay, here, when you are hanging 20 Newton, your extension actually is 10 cm. Okay, when you are hanging unknown W, what is your extension? Your extension is 20 cm. So in your mathematics ratio, year 7, learn ratio. Here 10 become 20, actually it's times 2. So your left hand side also need to times 2. So what is your weight? 40 Newton. This is mathematics way. Just now method 1 is actually physics way. Find the spring constant, apply in the formula. But another method to solve the question using a mathematics ratio. Okay, any question dear? No, can we proceed to the question number 3? Okay, if I'm too fast or you haven't able to write it down, you message me and let me know. Okay. For me, what is the spring constant? Okay, Angeline. Correct. Angeline, correct. Angeline, can you tell me how you do that? Zihua, correct. How about others? Spring constant. What is the value for K? How about others? Okay, you see, F equals to Kx. Let's say, I using the weight is 5 Newton, and then minus, oh, okay, same as me, Angeline. Emily, no. Okay, dear, you look at me, if let's say I'm using this as my data, 5 Newton equals to the K. What is my extension? Extension should be the new length minus original length. What is my original length? 12. When there is no load. Okay, the length actually is original length 12. So minus and K, I get 0.19. Dear, is it 0.19 is my answer? Newton per cm. My answer is no. Answer not C. Not C. Why not C? Teacher, you count everything seems like makes sense what? But my answer is donkey. Why donkey, dear? If you're using 5 Newton, we don't know that whether this force is actually exceed your limit of proportionality or not. We don't know. Is it already, the spring is already spoiled? At 5 Newton, is it already spoiled? So we cannot using 5 Newton as our answer to do calculation. It might be already spoiled our spring. So what can we do is we using this one, the 2 Newton one. Okay, so this is not a good idea if you're using the last weight as your calculation. Okay, it's already exceed your limit of proportionality. Okay, so what should I do? F equals to Kx. 2 Newton equals to the Kx. X is extension 20 cm minus 12 cm. So your K should be 0.25 Newton per cm. Okay, just now I already tried to count. If I using 2 Newton and I using 4 Newton, 4 equals to K 28 minus 12. Actually, if not mistaken, this one K I also get 0.25 Newton per cm. But when I'm using the 5 Newton, it didn't get back 0.25 is because this one, the Newton, actually is already spoiled the spring. Okay, so the seventh way is we're using small loop to do calculation for the spring. Okay, is that clear? Answer is donkey. I want to emphasize here, zero load. This one 12 is original length. They don't tell you, but you have to know from the graph, from the table. Okay, any question? If no question, we want to go to question 4, page 6. Is it okay? No response, dear. Crystal, okay. Megan, okay. So don't using the largest value. It might be already greater than your limit of proportionality. Okay, dear. Next, extension load graph. Okay, extension load graph. So here, unstressed length, dear, unstressed length. So what is this? Original length. Unstressed, that means that original length. Okay, when the object is hung from the spring, the length become 19.2 cm. What is the weight? They provided the graph. That means that you can get the data from the graph. Like, dear, try and then tell me what is your answer. Zihua, no? Hmm? Wait lah. Okay, here, this is new length. Here, the graph is giving you extension. So we need to find the extension. Extension is new length minus original length. New length is 12, 19.2 minus 17. So your answer should be 2.2 cm. This is not our final answer yet. It's not our final answer yet. From here, we can get the answer from the graph. Angeline, correct? So 2.2 extension. So that means there's somewhere here. Okay, from here going down. So answer should be 3.0 Newton. You see, answer is in 3.0 Newton, not 3 Newton. It's because in physics, we're trying to give the answer 2 to 3 significant figure. Okay, so dear, here, because the graph is extension, so we need to find extension. We need to find out the extension, only able to use the data from the graph. Answer is donkey. Okay, if no question, we go to page number 7. Is it okay? Is it okay, dear? Yes, okay. So here, diagram show the spring and a graph of the length of the spring against the load. Length against the load. Teacher, you're not telling us that this graph is directly proportional, man? Must be a straight line passing through origin, what? Why, teacher, this one is not starting from 0, leh? Any of you can tell me why this graph is different as what we learned just now? All the graph is directly proportional, but why this graph is starting from somewhere here? 2.5. Why? Any of you? Zihua said because this is length to load, not extension to load. Angeline said both the length and the load also does not start from 0. No, Angeline, your answer no. Zihua answer is correct. Emily said that because this is length against the load. Yes. Dear, be careful. This is called length against the load, not extension. Extension is we already minus the original length. So you look at this. When it is at 0, what is your length from the graph at here? 2.5 cm. So when the load is 0, the length is 2.5 cm. What is this length? Original length. That means that from here to here, this is original length. They didn't minus it. What we learned just now, all is extension. It's already minus original length. We already do calculation for it and then we plot the graph. But for this one is we didn't count for you for the extension. We're starting from the length. We measure the length. Okay. So at here, what is the extension of the spring when the load is 40 Newton? Okay, 40 Newton, what is the extension? Calculate and then tell me. Correct, Angeline. How about others? 40 Newton. 40 Newton. So this one we don't need to do anything. It's because this is load. It's already what we want to find. 40 Newton. So here, let me check your answer. Emily correct. Zihua correct. 40 Newton, we go up. Okay, then we go here. 4 cm. Is it 4 cm is our answer? No. 4 cm is what? The length. 4.0 cm. Question asking what? Extension. So extension is new length minus original length, which is 4.0 minus 2.5 cm. Your answer should be 1.5 cm. Okay, so boys and girls, please be careful on how you, on the question is the length or actually is the extension. Okay, Megan, did you get my idea? Megan, check which part your idea is wrong. Then we correct it. Okay, if no question, we go to page number 8. Is it okay? Can we proceed to the page number 8? Next week, we will do the paper 6 about Hooke's law. You must please make sure you print out, then you choose actual size. And then print out because we need to using a ruler and do some measurement. If you didn't print in scales in actual size, at the end your result when you do measurement, you will get a wrong answer. Okay, dear, we proceed to the next page. Okay, what is means by extension? Extension meaning that we're using new length minus original length. Okay, so extension basically somewhere here to here. This is called our extension X. Okay, when the graph of extension against load is drawn for the spring, the result is in the line. Okay, unstressed length again. What is this? Original length. Keyword unstressed is original. Okay, calculate the total length of the spring when 5 Newton. When 5 Newton, what is your total length? Right? Boys and girls, 2 marks. Tell me your answer. Can you go back to the page? Yes. This one? Okay. The rest of the boys and girls, 6B1. Calculate total length. You do calculation right now. Okay. Angeline correct. Zihua correct. Okay. 5 Newton. From the graph, we can see 5 Newton. So you need to show on the graph going up until the line. Then from here, go here. Okay. Until here, you get extension 2 cm. Extension, this is extension. Emily, correct? Here, extension, but they want you total length. Total length should be your original length plus your extend. Okay, how much you extend the spring? So original is 9 plus you extend 2 cm when 5 Newton. We hang on it. Okay, so it will be 11 cm. Okay, is that clear? Find the extension that will be caused by a load of 2 Newton. Okay, 2 Newton. When 2 Newton, what is the extension? When 2 Newton, what is the extension? Correct, Angeline. Emily, correct. Remember here, 2 Newton go up. Oops. Where 2 Newton go up. Okay, here, come here. So this answer is 0.x cm. So your answer is 0.x cm. You see, if they didn't give you any space, actually normally is no calculation is needed. If they give you too much, supposedly we have some calculation. Can you calculate the mass of a load of weight 2 Newton? They give you the weight, asking you to calculate the mass. This one is previous chapter, related with the formula W equals to mg. Your weight is 2 Newton. Your mass, we don't know. Your G, they didn't tell you, but in our syllabus, they assume you know that. Okay? So at here, Angeline, now new syllabus, we're using 9.8. Let me check. Maybe it's still 0.2. Let me check. 2 divided by 9.8. Oh, yeah, correct. So m equals to 0.20 kg. 20, if you write 0.2 kg, I will give you wrong. 1, 2, 2 significant figure or 3 significant figure. 0 point in front of the point is 0. The 0 doesn't count as significant figure. How you count significant figure? This one is mathematics. Ask your mathematics teacher again if you don't know. 0.20 kg. You see, if they didn't give you unit, please, you have to write unit by yourself. Okay, we go to your next page, page 9. Is it okay? Crystal, Shuan, Emily. Okay, so we go to page number 9 right now. Okay, here. So initially we hang with the we didn't hang any object, so we get the 29.8. Then after that we hang a load 5.5, we get 62.8. Okay, what is the extension? Easy lah, this question. Extension is new length minus original length. New length is 62.8 minus 29.8. So at here, press your calculator. Blah, 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 blah. Okay, we will get 33 cm. Okay, no need to purposely convert cm to m because that question doesn't mentioning. Write your answer in SI unit. If SI unit, there will be in meter. Okay, here the law that relate the extension to load is load constant times extension. The load actually is force. They're asking you what is your spring constant? What is the K value? So from the diagram, what is your force? What is your load? This is your load, 5.5. So we put in here 5.5 equals to the K, we don't know. Numerical value, that means magnitude. Okay, the number, the magnitude. So X extension, just now here we already do calculation for the extension, 33 cm. So your answer at here, K should be equals to, let me count. Okay, if I want two significant figure, it will be 0.17 Newton per cm. Make sure correct, because this 33 is in cm. This is in Newton. Okay, two significant figure, then 0.17. If three significant figure, your answer can be 0.167. Okay, so here 0.17 Newton per cm. So this one is 33 cm. Right, suggest a suitable unit for the constant. So at here, Newton per cm is our constant. If you convert the cm 33 cm to 0.33 m, then it will be Newton per meter. Okay, so for this question, actually, it's easy because we did a lot of the question in the MCQ. Basically, it's the same thing, but make it in the structure only. Any question for this question number 7? Force, load is force, or maybe the weight. Now they're talking about weight, or maybe they didn't give you the weight, force, load. They give you mass. If they give you mass, then we have to m times g. Any question? If no question, we goes to the last one. Last patch. Okay, last patch is here. The length of the spring is measured when various load from 1 Newton to 6 Newton are hanging from it. Okay, figure below show the graph. Use the graph to find the length when the spring or length of the spring with no load attached. No load attached. What is your length? My dear, what do you think? Correct, Angeline. How about others? Do you know how to find? Teacher, I don't know. When no load. No load attached, that means that the load is 0. When load is 0, what is your length? Zihua correct. So dear, you should put your ruler like this. You should put your ruler along the line. Okay. Then after that, you draw the line. Continue, draw the line. Yeah, something like this. Okay. So what is this reading? So this one 8, 6, 7, 6, 7, 8, 9. This is 9. Here is 8. Call length. When no load, no load. Okay, this length actually called original length. Okay, second question. Length of the spring with 4.5 Newton. What is your length of the spring with 4.5 Newton? Okay, do it right now and tell me your answer. Zihua correct. Angeline correct. Others? 4.5 Newton. So from the graph, Newton is load 4.5. So it's here going up. Then from here, go here. What is this answer? 15, 16, 17, 18. This is 19. So your answer should be 19 cm. Let me check. Megan correct. Emily correct. Okay, what is the extension caused by 4.5 Newton? This is called length, but what is the extension? My dear, tell me what is the extension? Angeline correct. Megan correct. Okay, extension is your new length minus original length. This is original length. This is your new length. So you're just using 19 minus 8.5. 10.5 cm. 10.5 cm. Okay. So basically, we complete our lesson today, lesson 14. Next week, we will continue the lesson 15 and 16. Okay, you get ready for the worksheet, and as I told you, print it out in actual size. Okay, so any other question? If no question, then we will stop our lesson today.